Francis is an expert on the origin and evolution of solid body surfaces and interiors across basically the entire solar system. He received his PhD from Cambridge University in 1986 and is now a professor at University of California in Santa Cruz. And today he'll be talking not about one body, but about an entire family of ocean worlds. So he has an unenviable task. And he'll touch on how geodetic measurements can help us figure out the origins and evolutions of these enigmatic worlds. So take it away, Francis.
I'm going to be talking about ocean worlds, and really what I want to do is to do two things. I want to provide a resource for people to understand the basics, but I did also want to pose some questions that will kickstart the discussion in the workshop next week. So why do we care about ocean worlds? One thing is that they're actually surprisingly common. There are a whole bunch in the outer solar system, and the more places we look, the more we find. They're very interesting from an astrobiological point of view because they're regarded as potentially habitable environments. And in some ways, I'm not going to discuss this much, but moons are intrinsically more complicated than planets. So for example, the thermal evolution of a moon is coupled to its orbital evolution, whereas for a planet, thermal and orbital evolution are decoupled. And then, as I hope to show, these ocean worlds present a very rich set of geodetic problems that we've only just started to address. So I'm going to start out by talking very briefly where we think there are ocean worlds right now. And then the bulk of this talk really is going to be discussing how we detect subsurface oceans, both in the past and with future measurements. I'll briefly talk about how you can measure active deformation, because many of these worlds are probably undergoing deformation at the present day. And I'll talk a little bit about, once we've detected the ocean, how we can go about characterizing the properties of that ocean. And then I'll finish with a couple of slides on the issue of habitability. So that's our roadmap. So like I said, ocean worlds are common. This is a montage of the satellites of the outer solar system to correct relative scale. You can see the Earth's moon for scale. But the point is that the ones in blue are the ones where we're pretty sure there is a subsurface ocean. So Europa, Ganymede, Callisto, Enceladus, and Titan, we're pretty sure have oceans. And then other bodies like Triton or Pluto may also have subsurface oceans too. So there are a lot of presumed oceans out there. And so really the heart of this talk is to discuss how we go about detecting them. And I'm going to go through this whole shopping list of different possibilities. The first three we've already used. We used magnetic induction, librations, and obliquity to detect oceans. And then these other ones are potential techniques that haven't actually been used yet. And so I'm going to go through each one of these in turn. The very first one, it's not really what I would call a geodetic technique, but it's very powerful. And so the basic idea is that Jupiter's magnetic axis is offset from its rotation axis. And so as Jupiter spins, Jupiter's magnetic field gets swept around. And so a body like Europa experiences a changing magnetic field. And if Europa is conductive, then that changing external field induces currents which produce a secondary and induced field inside Europa. Galileo, when it flew past Europa, detected this secondary field, and the amplitude of that secondary field tells you how conductive Europa is, okay? And so this is just a little schematic. You've got the primary field, which is time varying, in a conductor that produces eddy currents, that generates a secondary field that opposes the primary field. And so we can measure the secondary field. And what was found is that the conductivity that you get is consistent with a shallow, salty ocean. Salt water is quite conductive. And so this is a very good way of detecting subsurface oceans. Unfortunately, it doesn't work at Saturn because Saturn's magnetic field isn't being swept around, but it would work great at either Uranus or Neptune if you sent a spacecraft there. Okay, that was induction, which isn't really geodesy. I'm now going to get into geodesy, and I'm going to start by talking about tides. And so if you have a satellite close to a big planet, then the near side of the satellite experiences a slightly bigger gravitational attraction, and the far side experiences a slightly smaller gravitational attraction. And so the satellite develops a tidal bulge, okay? So they're distorted by tides as well as by rotation. And the really crucial, or at least one crucial result, is that the size of this bulge, how distorted you are, you can relate to the moment of inertia through this magic equation called the Darwin-Banach equation. This works as long as the body is behaving like a fluid. If you can ignore the elastic effects, then just from measuring the size of the bulge, that tells you the moment of inertia. And the moment of inertia is important because it tells you about the distribution of mass inside the body. And so this is just one example for Europa. What I'm showing on the horizontal axis is a gravitational measure of how big the tidal bulge is. So the horizontal axis is just basically the size of the bulge. And then the vertical axis, it's being interpreted as the thickness of the ice plus water, the hydrosphere. But you can really think about this as just the moment of inertia. And so as you change the distortion of the body, you get a different moment of inertia, and you can interpret that as a different ice plus water thickness. And so just by measuring the shape, the distortion of the body, or the gravity arising from that distortion, we can derive things like the thickness of the hydrosphere. If the body is acting like a fluid, it has to be hydrostatic. Anton mentioned this, that as long as you can ignore elastic effects, then you can use this magic equation to go directly from the shape to the moment of inertia. So this is a very powerful sort of basic constraint. But there are lots of other things we can use tides for. And one is that with many of these objects, the distance to the planet changes. They have eccentric orbits. And so if the distance between the satellite and the planet is changing, then the bulge will actually swell and shrink and swell and shrink over the course of an orbit. And so that's what I'm trying to show here. When you're close to the planet, your tidal bulge is large. And when you're far away from the planet, your tidal bulge is much smaller. And so there's a time variable part of the tidal bulge. Very often when we think about this kind of a problem, it's actually useful to think about a reference frame located on the satellite. And so if you put yourself on the satellite, what you see is that the planet executes a little ellipse in the sky overhead. And so when the planet is close to you, you're very distorted. And then when the planet is further away from you, you're less distorted. And so you see the planet moving backwards and forwards in the sky overhead. And as a result, your tidal bulge gets bigger and smaller. These are called diurnal tides because they happen once a day, once a rotation period. Okay, one of the reasons that this is important is because you're going to get torques. If the planet is in line with the satellite, then it's not going to exert any torques. But when the planet moves off the line, then you've got this distorted satellite, the planet is over here, and so you're going to experience an anti-clockwise torque, and then half an orbit later, you're going to experience a clockwise torque. And so over the course of an orbit, the satellite experiences these periodic torques, and if you apply a periodic torque to a body, that causes the rotation rate to change. And so the satellite is actually going to wobble backwards and forwards around its mean rotation state. And those are called physical librations. And the really important point about physical librations is that they tell you about the internal structure of the object. So this wobbling backwards and forwards tells you something about the internal structure. So, like I just said, these librations, they're periodic variations in the rotation rate. And the key point is that the size of that variation, the amplitude of the libration, tells you whether or not there's an ocean underneath. If you have a solid object, then the libration amplitude typically is quite small. But if you have the same object with an ocean or a liquid core on the inside, then the libration amplitude is much larger. And that's just because your torque is being applied to the shell, which has a smaller moment of inertia than the whole body. Same torque, smaller moment of inertia, you get a larger libration amplitude. And so this is a good way of detecting internal liquid layers. It's been used at Mercury. That was one of the ways in which Mercury's liquid core was discovered. It was also used to detect an ocean at Enceladus. Through bad luck, this technique actually doesn't work at Europa. It's not anything fundamental. It's just that the parameters worked out in a bad way. So it doesn't work at Europa, but most other places, this approach of looking for the periodic variations in rotation will allow you to detect a subsurface ocean. Okay, another rather similar approach is to make use of the obliquity, which Ali also talked about. And so the obliquity is just the angle between the rotation axis and the normal to the orbit plane. So if you have a synchronous body like the satellites that are being tidally torqued, then you can actually predict what the obliquity should be. It's not a free parameter. You can actually predict it if you know the moments of inertia. This is something called a damped Cassini state. So if we know the moments of inertia, which means knowing the gravity field, we can predict the obliquity. And what we would expect is that if there's a decoupling liquid layer inside, the obliquity will be bigger. And that's again simply because now you're talking just the shell rather than the whole body. And so the obliquity is predicted to be bigger than if you're talking the entire body. So we can make these measurements. You can make the measurements from Earth by using a big radar. You might even be able to do that by for the Galilean satellites with an Earth-based radar, or you can do it by spacecraft. And so the one place in the outer solar system where we've done that is Titan. And so the red line is a schematic of the measurement at Titan. And what you can see is that the observed obliquity is much bigger than the predicted for a solid Titan, but it's about right for a Titan that has a subsurface ocean. And so the large obliquity of Titan is telling us that it has a subsurface ocean. And this is the strongest piece of evidence that we have for an ocean on Titan. Okay, coming back to the tidal response, I talked about the fact that the periodic variations in the tidal bulge happen if you're in an eccentric orbit. And the amplitude of that deformation is described by these dimensionless so-called love numbers. They just tell you how much the tidal bulge changes over the course of an orbit. Here is AEH Love with his splendid Edwardian moustaches. So the important point again is that if you have, for instance, a rock layer bound to the ice, then it won't deform very much. Whereas if you put a decoupling ocean in between the rock and the ice shell will deform much more, and so it will have larger love numbers. And so by measuring the love numbers, you can tell whether or not you have a subsurface ocean. K2 and H2 are slightly different in that K2 just tells you about how the gravity changes in response to these tides, whereas H2 is telling you how the surface itself actually deforms in response to these tides. And typically K2 is a little easier to measure than H2 because H2 needs an altimeter. And one other point to remember is that in reality, these love numbers are actually frequency dependent. And so if you're making measurements at different frequencies, you have to be a little careful. But the main point is that by measuring K2 or H2, you can tell the difference between no ocean and an ocean. For the case of an ocean, what the love numbers are really sensitive to is the thickness of the rigid shell. If you have a very rigid shell, it's not going to deflect very much. If you have a very thin or a weak shell, it'll deflect a lot more. And it turns out that even though you can get information from either K2 or H2, it actually really helps to be able to measure both. If you can measure both, you get more information. And this is a slightly complicated plot, but what I'm showing you here is K2, that's the single love number, and then this funny thing delta, which is 1 plus K2 minus H2, which is a combination of those two love numbers. And so let's say you measure a K2 of 0.24. You can read across, and you would guess that if you were on this black line, the shell thickness would be, I don't know, 15 kilometers or something like that. But if you pick a different ocean density, you would get a much larger shell thickness, something like 40 kilometers. So if you just measure a single love number, there's an ambiguity between the thickness of the shell and the density of the ocean. So there's a nasty trade-off. But if you measure both K2 and H2, say it's 0.08, then you'll say, okay, the shell thickness is about 30 kilometers, and you don't care what the thickness of the ocean density is. And now the ocean density isn't introducing an ambiguity. So this is showing that there's a real advantage in measuring both of those love numbers because it reduces the numbers of trade-offs. Okay, Peter talked about static gravity and topography, and so did Anton. And this is actually a diagram very similar to what they showed. But the point is that you can use measurements of the gravity to distinguish between a thin shell and a thick shell. If you have a thin shell, then the mass excess and the mass deficit are close to each other, and so they almost cancel out, and so you get a rather small gravity anomaly. But if you put your mass deficit much deeper, then attenuation means that you won't sense so much of it at the surface, and so you get a much larger surface gravity anomaly. So simply by measuring the topography and the gravity, you can get an estimate of how thick the shell is. Is it thick or is it thin? And in detail, you can do that using this admittance technique, which is just taking the ratio of the gravity and the topography over different wavelengths, like Peter mentioned. Things can get more complicated. One problem is that you may not be in an isostatic situation, which is what's depicted here. If elastic thickness, if flexure is important, that makes the calculations more complicated. And then something that Anton mentioned is that if you have a deep root, then that root may tend to flow out sideways. And so that will also, again, change your interpretation of the results. Nonetheless, this is a very good way of probing the structure of the ice shell. And one place where this has been done very successfully, for instance, is at Titan, where we have measurements of both the gravity and the topography at very low degrees. It may be an obvious statement, and I'm certainly not a seismologist, but you can use seismology to probe things like the thickness of the ice shell. And so this is just a single example, but basically what it's showing is that if you have different thicknesses of ice shell, then the dispersive nature of the seismic waves will change. And in particular, the peak in the group velocity kind of scales with the travel time of seismic waves across the shell, which is sort of more or less what you'd expect. So a seismometer can certainly infer shell thicknesses if you have sufficiently good seismic sources. You can also use a seismometer either as a gravimeter or indeed as a tilt meter. So if it's a gravimeter, then it's measuring some combination of H2 and K2. And if it's a tilt meter, it's just telling you how the surface is deforming. And so this is just an example of some calculations for the tilt that you see on Enceladus. And the main message here is that the tilts are rather small. These tilt angles are a few microradians. And so that tells you the kind of accuracy that you would need to be able to detect these signals. Classical geodesy is often concerned with rotation variations, as Anton mentioned. And so I'm just going to talk about a couple. The first is the so-called Chandler wobble. The Chandler wobble is when the solid surface of the Earth slops backwards and forwards around the rotation axis, which is fixed. And so the surface of the Earth is actually wobbling backwards and forwards around the rotation pole. This is sensitive to the presence of liquid layers. And so in principle, it could be used as a probe of liquid layers on icy satellites. And a tour de force recently is that Alex Konoplev detected the Chandler wobble on Mars, and the amplitude of the Chandler wobble there is of the order of centimeters. So that's a remarkable result. On the Earth, the way it was originally detected was by looking for the apparent variation in the latitude of the stars as the solid Earth moved. And you could presumably do something similar if you had a lander by tracking stars. Another class of rotation variations is the so-called nutation. So the rotation axis in general precesses, right? The Earth's rotation axis is precessing, but superimposed on that precession, you can get these shorter wavelength wobbles backwards and forward called nutation. And that's just because if you give a spinning top a little kick, that kick, it won't die out. It'll keep moving superimposed on the background precession. And the point about the nutation is that, again, this is sensitive to the presence of subsurface liquid layers. So this is sort of classical geodesy, and these provide ways of probing for subsurface liquids. And then there are some more sort of outlandish ideas. One is that you can use astrometry, which is the rate at which the orbit of the satellite is evolving. And one of the things that that orbital evolution rate cares about is the satellite's K2 and also its Q. Q is a dissipation factor that I'll talk about in a minute. But the main point is that if you have an ocean, you expect more dissipation and more tidal deformation. And so qualitatively, you expect a larger K2 on Q if there's an ocean. Similarly, it's not obvious, but it is the case that if you have an ocean, then you can damp the orbital inclination much more rapidly than you can damp the eccentricity. And so if you see an object that has a damped inclination, that might be another indication that there's a subsurface ocean. The problem with both these techniques is that they are kind of semi-quantitative. You can't really do a precise job, but there are at least indicators that there might be a subsurface ocean there. All right, I'm going to take a 30-second pause and let everybody catch up. Okay. So I want to switch now to talking about detecting active deformation. And if you remember this little plot that I showed you before, then the size of the tidal bulge changes over the course of an orbit. And so the surface deformation that you see will be time dependent. And so if there are fractures on the surface, they'll open and close over the course of an orbit. And so the famous example of this is the plumes on Enceladus. Those plumes get brighter and less bright over the course of an individual orbit. And that's presumably because the tidal stresses are opening and closing cracks. We all like to assume that bodies are spherically symmetric because that's easy, but of course, in reality, there are likely to be lateral variations in material properties. And so that makes life much harder. People like Harriet Lau can do those calculations, but they're much more complicated than if you can assume spherical symmetry. So you can go ahead and predict what the surface deformation should be like. And so these plots here are for an example on Enceladus. And you can see that if we assume spherical symmetry, then the deformation is of order a meter or so. Whereas if you allow the material properties to vary and you make the south pole weaker, then the amplitude of the deformation can get larger locally. And so there are various ways we could think of measuring this surface deformation. We could use altimetry, we could use gravity. If we have a really, really good camera, we might be able to use imaging. But I'm going to focus on the last two, which is radar interferometry and using assets at the surface. And just another point is that, as you can see, as we introduce lateral variations in material properties, the wavelength of the deformation gets smaller. If you have spherically symmetric bodies, then the wavelength is all rather long. It's degree 2 or degree 4. All right, so radar interferometry. Peter showed a nice example from the Earth. This is a neat simulation of the kind of interferogram that you might see on Europa. These are the 3 components, the 2 horizontal and the vertical, and then what you see in the line of sight. You can see that the deformation is of order centimeters. And so in principle, this is a very good technique for looking for active deformation. I think the big technical hurdle is that you require very precise orbit knowledge to be able to do these repeat passes and form your interferograms. But this is a good way of detecting local deformation. And then we can think about what we could use in the case of surface assets. I've already talked about seismometers and gravimeters. We could use laser reflectors, which Anton mentioned briefly. The latter have been very successful on the moon, partly because we have an observation span of 40 or 50 years worth of data. And in general, these surface assets give you higher precision than orbital measurements, but the problem is that they're very spatially restricted. And so if you have a complicated deformation field like here, you'd really like to get not just a point measurement, but a series of measurements or a global view. In any case, with a surface asset, there are a whole bunch of things you could measure. You can measure the librations, the obliquity, rotation rate variations. You might be able to do induction. You could certainly look for local tilt. And so a surface station could do geodesy of a really different kind than the kind we've done so far on the icy worlds. Something I want to talk about briefly is that in general, the tidal response of a satellite is not instant. There's generally a lag between the forcing and the response. And so the tidal bulge doesn't point directly towards the planet. There's a phase lag. And this phase lag is very important. It can cause torques, it can cause tidal heating, and it can cause the orbits to evolve. And the way that we describe this phase lag is by this famous dissipation factor Q, and Q scales as 1 over the phase lag. So a small phase lag means a big Q means small dissipation. Like I said before, the tidal heating rate scales with K2 divided by Q, or if you prefer, the imaginary part of K2. But the point is that a low Q means a large phase lag, and both of those mean a high heating rate. So Q tells us something about the internal structure of the body. And in particular, it tells us about the viscous response of the body. And so if you have a very viscous material, it's going to behave elastically and the phase lag will be small. If you make the viscosity smaller, it'll start to have a larger phase lag. And so that's what's being plotted here. This is the phase lag as a function of the viscosity of ice. And so if the ice is very viscous, it behaves elastically and it doesn't give you any phase lag at all. But as you crank down the viscosity, the phase lag increases. And so if you measure a phase lag, it's telling you something about the viscosity structure. But the reason that there are multiple lines here is because it also cares about the thickness of the ice shell. If the ice shell is thin, it's just not imposing a very large amount of viscous response. Whereas if the ice shell is much thicker, it's imposing a much bigger viscous response. And so the phase lag in principle can tell you also about how thick the ice shell is. I've talked a little bit about tidal heating, and an important point is that tidal heating is spatially variable. And so that means that different places on the surface experience different amounts of tidal heating. And so somewhere like Enceladus, we can actually see the heat coming out, and so we can look for that spatial variation. But even if we can't measure it directly, we can use inferences to get at it. And in particular, if there's a lot of tidal heating, you'll get a thin ice shell. And if there's less tidal heating, you'll get a thick ice shell. And so we expect the shell thickness to vary. And by isostasy, that means we expect there to be topography. And so this is just an example of the kind of topography that you'd expect to see on a tidally heated body. And basically, at the poles, the tidal heating is high, and so you get low topography. And at the equator, the tidal heating is lower, and so you get higher topography. And the amplitudes can be quite large. They can be, say, a kilometer or so. And so this topography would be arising from the spatial variations in tidal heating. An interesting result is that if you have tidal heating in the shell, that gives you this pattern. But if you have tidal heating in the ocean or in the core, you'll get a different pattern. And so if you can get the pattern, then that might tell you where the tidal heating is actually happening. But there is, of course, a complication, which is that the ocean is probably rather good at redistributing heat. And so if the ocean redistributes heat from the core, then you can't necessarily use the pattern of heat flux that you get to tell you about what the core is doing. Okay, well, I want to move on to oceans. And so how do we go about getting ocean properties? And right now, by far the best way of getting the ocean properties is to use induction. And this is because if you can measure the induced field at different frequencies, you can simultaneously solve for the thickness of the ice shell and the thickness of the ocean. And this is what Europa Clipper hopes to do. Things get easier if you have both a lander and an orbiter, as has been done at Mars with the MAVEN InSight combination. And so induction sounding is very powerful, but again, I don't regard this as strictly a geodetic technique, and so I'm not going to spend too much time talking about it. Instead, what I'm going to do is just give you 4 ideas, all of which are fairly outlandish, but I think they might be fun to talk about next week. So the first one is that oceans are actually different from solid bodies because they have inertia. If you start an ocean moving from a tide, it'll slosh around, right? It won't come to a rest instantly. It has inertia, and so it may overshoot and slosh backwards and forwards. And that's different from a solid part of the planet. And what that means is that this sloshing effect can give rise to phase lags. Here's the phase lag. And this, I'm showing it as a function of the ocean thickness. And so in principle, if you can measure the phase lag, that would tell you something about the thickness of the ocean. Notice that these different colors are for different ice shell thicknesses, and they don't really matter. So in principle, if you could measure the phase lag, that would tell you the ocean thickness. Unfortunately, these panels are for different degrees of the total amount of dissipation in the oceans. And so as you dial that parameter up and down, you change the phase lag. And so there's this trade-off with the degree of dissipation assumed. And so that's a problem, but nonetheless, this might provide you with some information. The second one, I want to come back to this idea of induction, but now I'm talking about induction because the ocean is moving. If the ocean is moving in a steady background field, a moving conductor in a field creates an induction current and an induced field. And so in principle, you could use this to detect ocean currents. And this has actually been done on the Earth. We can measure ocean currents on the Earth by looking at the induced field they create. The problem is that the effects are small. So this is the regular term. This is the fact that you have a time variable primary field that gives you an induced field of about 250 nanoteslas. This is the field because the currents are moving, and this gives you an induced field of maybe a nanotesla. And then there's a final effect, which is because the magnetic field lines are getting stretched by the tidal distortion, and that's even smaller. And so in principle, this is a good idea, but it's just the magnitudes of the fields that you expect to see are very small. Something that I think has a lot of future is the fact that if the ocean has currents, then those currents will impose torques on the shell. And so this is very like the situation we have on the Earth, where the currents in the Earth's core can produce torques on the Earth's mantle, causing so-called length of day variations. And so Bruce Buffett has thought about this a lot on the Earth. Oscar Karatekin has thought about this for Titan. But the point is that we'd expect to see variations in rotation rate coming from ocean currents. And so this is a calculation that Gary Glatzmeyer did a long time ago, looking at the torque that the ocean currents are producing on the shell. And the important point here is that these torques don't actually sum to zero. You get a steady torquing of the shell over time. And so in principle, this kind of steady torquing is the kind of thing that you might actually be able to look for. And then another even more outlandish idea is that we don't know whether the oceans are stably stratified or not, but they might be. You might have a sort of low density with a high density salty layer below. And if that happens, then you can get internal gravity waves. You can get a disturbance in the interface that then propagates. And that, of course, will give a surface gravity signal or a surface deflection that you can in principle measure. And the reason I bring this up is that this has been done on the Earth. This is very clever. So you have an atoll with a seismometer. This is the South China Sea. The South China Sea has strong internal gravity waves. As these gravity waves propagate past this atoll, you see tilts on the seismometer. This is a time series, and these red lines here are the tilts that you observe as the gravity waves go past. And so in principle, you ought to be able to look for these internal waves with something sitting on the surface. Okay, that was 4 crazy ideas. I'll talk very briefly about habitability, and then I'm going to finish. So for habitability, we need water. We've talked a lot about oceans. You need raw materials, and then you need an energy source. And, you know, in my view, it's hard to do much for habitability with geodesy. Certainly you can talk about the presence of water, but the raw materials thing is just very difficult. But we can think a little bit about energy sources. And in particular, we can think about whether the shell is able to transport raw materials around from the ocean to the surface or from the surface to the ocean. And so that matters whether the shell is conducting or convecting. And we can also think about energy sources like tidal heating or water rock reactions. So for conduction versus convection, the main difference is that the temperature structure is different. This is a plot of temperature versus depth. If you have a conductive shell, the temperature just increases steadily. Whereas if you have a convective shell, you have a cold lid, but then a warm interior. And the point is that these two structures will give you different tidal responses. And so on the right, I'm plotting this funny delta 1 plus K2 minus H2, and then the imaginary part of K2. And the point is that the convective results and the conductive results occupy different places in this parameter space. And you move up this line as you increase the thickness of the crust. And so if you can measure the love numbers, the real and the imaginary parts, you can distinguish between the conductive and the convective cases, and you can tell how thick the shell is. So that's potentially pretty powerful. In terms of tidal heating and water rock reactions, it's generally true that if you have a cold mantle, you'll probably get larger gravity anomalies than a warm mantle. So that's qualitative, but useful. A tidally heated mantle, a warm mantle, will produce a big phase lag, and it will also produce a different spatial heating pattern, as I suggested. And so that's something you might be able to look for. And then just to remind you that we know now that the silicate core of Enceladus is so low that either it's very porous or it's been hydrothermally altered. And so, you know, these are not just hypotheses. Enceladus is a place where one of these things has probably actually happened. And just as a last idea, when we're thinking about separating out the core from the mantle, I talked about the librations before, and it turns out that the shell will librate at a different amount to the core. And so this is potentially interesting because if you have a lander, the lander is fixed to the shell, and so it won't be sensitive to the shell librations, but it'll see the core rocking backwards and forwards underneath. Whereas an orbiter will see both the shell and the core librating. And so if you have both an orbiter and a lander, you'll see different variations in the gravity because of these differential rotations between the core and the shell. And this is just, these are some calculations by my student Wencheng Xiao, showing that the amplitude of the shell libration is quite different from the amplitude of the core libration. All right, I know that was a lot of information, but let me now just summarize. So I spent a lot of time talking about how we can use geodesy to detect oceans. There are many techniques, some of which have been used successfully already. Characterizing the oceans as opposed to detecting them is hard, but I think it's doable, particularly if you can get really good measurements of the tidal response. Talking about habitability by geodesy alone, I think is very hard, but you know, maybe someone in the audience will have a good idea of how to do that. I think the physics of rotating fluid-filled shells and how they couple to the solid ice to produce things you can observe is a very rich area for future research. And we're starting to get the technology that can actually measure some of these things on real satellites. So I think this is a good thing to be thinking about. And then the last is that if you have a combination of measurements taken at the surface and at orbital altitudes, you can do a lot more than with either alone. And so let me leave it there and I will take questions. Thank you.